Okay, so you're going to write an equation for a parabola with focus 1, 2 and directrix at x equals 5. So for a parabola, for any of our conic sections, we're always going to have an x minus h and a y minus k. You're going to see that set up in any of the conic sections. For a parabola, we're going to put an equals between them. So on this question, our vertex, when we find it, is going to give us our HK, our reference point. For a parabola, we need to know which side is squared. Is it the x side or the y side? And we need a coefficient, which is either going to be plus or it's minus 4c, okay, which is going to be the length of the lattice rectum. So on this one, what you want to do is just graph what you've been given, 1 across, 2 up, label that, that's a focus, and you've got a directrix at x is 5, 1, 2, 3, 4, 5. So that's a vertical line, that's your directrix. So to find the HK point, our vertex is going to be halfway between those. So it's here. That's our vertex, and it's at 1, 2, it's at 3, 2. So now I also know which way this is going to open. Which way is it going to open? Well, it must cup around the focus. It's going to be opening like this. That's telling me because it's going, there's the positive x-axis, there's the negative x-axis. This is going to be negative. And I always just stop for a second and consider this. If x was squared, it'd be up and down. So this must be y squared. So which side is squared? The y side is going to be squared. I know my coefficient is going to be negative, and I know it's going to be 4c, but I don't know how big 4c is. So I know this is going to be x minus 3, y minus 2, and I do know 4c just by looking here. C is your focal length, which is the distance from the vertex to the focus or from the vertex to the directrix. And you can see there, that's 2. Our C equals 2, that's our focal length. So our focal width, the width of the parabola through the focus, is always going to be 4 times C. So it's going to be 8. And this gives us our coefficient. So our coefficient is 8, and I know it's going to be negative because of the way it opens. So I can put it here. That's one great version of the equation. Or I could have written that as x minus 3 equals negative 1 over 8, y minus 2 squared. And I'm happy with either of those. To graph this, the focal width, your lattice rectum, is 8. So at the focus, it's going to be 8 wide. So I'm going to go up 4 and down 4. Through that vertex. Okay, so there was your warm-up. Hopefully that made some sense to you. Right, there's a few, when you're working with parabolas, I don't think graphing them's too bad once you've got this whole concept of which way they open and this idea of pulling out C or 4C that gives you C from the equation. The part I think you really need to practice on parabolas is completing the squares, and completing the squares to get an equation in graphing form is something we're going to have to practice on every single one of the conics. We're going to do a little bit of practice with them every single day. It's the part that I think most people are going to go a little wrong with. Okay. So today we're going to start a new conic section. Today we're going to start looking at ellipses. Now, how you get an ellipse? I used to have all these links to coolmath.com, and they had lovely animations, but they were all flash driven, so we can't watch them anymore. To get an ellipse, what you do is you get the cone, a double nap cone, look at the angle at the side, and you cut it at an angle that's less steep. And the closer and closer you get to horizontal, the steeper the angle you cut it at, you're going to get a really narrow oval. If you cut it at an angle that's less steep, you get a slightly sort of fatter oval. And when you cut it exactly horizontally, you'll get a perfect circle. A circle is an ellipse. We just tend to write the equation a little bit slightly differently. There's a very big reason for that. So what we're on today, ellipses, is lesson 7.2, and we're on day 1. Now, this is just some of the stuff that used to be on coolmath.com that had great animations, but they're all gone. These ellipses have got some great properties, makes them really useful and quite fun. This is a horizontal ellipse. These points here would be called vertices. These points inside, they're not on the shape, but they give us the properties that are really useful. They're both a focus. And the plural for focus is not focuses. It's spelled like this, and I presume you pronounce that foci. If you say foci, I don't mind as long as you write it correctly. What's fantastic about ellipses is if you had something at this one focus point here, sending out a burst of energy, doesn't matter if it's sound energy, light, ultrasound, whatever it is, due to the properties of physics, the angle of incidence and the angle of reflection would be the same. And due to the geometry of the shape, any signal you send out from this one focus will be targeted and will go to the other focus. And not only that, if you add up the length of the path that energy has to take, wherever you reflect it off, that ellipse, it's always going to end up at the focus, and that distance you travel, d1 plus d2, is going to be the same anywhere for that ellipse. Depending on how fat the ellipse is, this number that will equal will be different depending on the size of the particular ellipse. But for one ellipse, the distance from this focal point to this focal point via the edge is always going to be the same, and anything you send out from this focus will arrive at that focus. And because the distance it has to travel is exactly the same, if you send out this burst of energy from here, all of the rest of the energy, all of the energy you send out will arrive at the other focus at exactly the same time, which means they have some fantastic properties. They use them in medicine to blow up kidney stones. You sit in a bath and you have your kidney here, this bath full of water, a three-dimensional thing, and they position you really carefully so your kidney, the kidney stone, is right at that focal point, and they send out a burst of energy, ultrasound energy from the other one, and it all reflects off the bath and it shatters the kidney stone inside your body. Now that terrifies me, but there's also another really cool application of them. It's called a whispering gallery. Now, whispering galleries, you don't stand up on a pole above the rest of the crowd. Everybody's standing at the same level. You have these thousands of people all standing here. But if these people are standing at the focus points, anything they say will be reflected off the ceilings and the side walls and arrive at the other focus point at exactly the same time. So I've not been to many of these. There's hundreds and thousands of them all around the world. I've been to this one, the Alhambra in Granada, in southern Spain. It was built sort of, talking about 900 years ago. And it's incredible. This place, between you, yes, you just stand at this one place in this big stone cavern underground, and you can talk in a normal voice like I'm talking in now. And this other person, they're probably about 150 yards away from you, miles away. And in between, there's thousands of tourists from all around the world looking around on their tours and all talking. But if you're standing here and another person's there, you can actually, you don't even have your back to them, it doesn't matter. Whatever you say, they can hear really clearly. There's other ones you can go to. One's in there's many in the States. The two famous ones are Grand Central Station in New York and the Salt Lake Tabernacle. Now, those are just fun applications of ellipses, but they do have other practical uses as well. So let's have a go at graphing one. So to graph an ellipse, now what I want you to do now is put this on a new page in your notes. We're going to graph it and then leave some space behind underneath it. We'll take some notes and we'll come back and we'll fill in some of the important details. To graph them, the first thing you look at is your HK point. X minus H, Y minus K. What is being subtracted from H is 1. What is being subtracted from Y is -4, and that will give you the center. Your HK point, your reference point on an ellipse, is going to be the center. Let's graph that. So 1 across, 4 down. That's going to be the center. Then you're going to draw this sort of oval shape, and how you know how far to go either direction to get to that is you look at this denominators. The denominator that's under the x minus h squared part, everything is squared. That's like it's under x, so it's going to give you a horizontal distance squared. Now later on we're going to call one of these a squared and b squared, but it doesn't at this matter. It doesn't matter which one's a squared and which one's b squared. We just know this is a horizontal distance squared. So take the square root of 16 to get 4, and that is telling you from the center horizontally go left and right 4, and that will take us to the edges of our ellipse. 1, 2, 3, 4. 1, 2, 3, 4. Remember, in an ellipse, everything is squared. So how do we know how far to go up and down? This is under y, and it's squared. So this is your vertical, because it's under y, your vertical distance out from the center, squared. So you take the square root of 64 and say, right, that is 8, and that tells you to go up and down by 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Now do your best job at trying to actually draw that ellipse. Go through those points. Ooh, I'm doing better. Getting better as the day goes on. Okay, so this told us it was underneath y. It told us to go up and down by 8. That's a basic ellipse. And when you look at that one, can you see that we would actually call this one a vertical ellipse? Because this length from this vertex to that vertex, we call that length the major axis, as in the longer axis. On this one, the major axis is vertical. How we could tell just looking at the equation is the bigger number was under y. The bigger number was under y, and so that's going to tell us that the major axis will be vertical. And how long is that major axis going to be? Well, we're going to call that length there a. This was actually a squared. So the major axis, we went from the center up 8, from the center down 8. It's going to be 2 times that length a. And how wide is this one? If I counted up that pink line, you'd see it's 16 spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Going across the other way, we call that the minor axis. And the length of this, we went 4 times 4 plus 4. The length is 8. And we're actually getting from that, if we're going to call that one A, we're going to call this one B. The smaller denominator is we call B. Some important points on here. On the major axis, the lengths of on the ends of your major axis, those points there, they're both called a vertex. So together we call them the vertices. And how we got there, we went up and down from the center. So we didn't change the x coordinate, but we got that -4 and we added 8. And we got that -4 and went down. Oh, and went down by 8. So these were at 1. -4 plus 8 is 4. And there's a second vertex at 1 -4 -8 -12. We have to put our foci on here. I'm going to come back to this. There's 2 points of the foci, and I'll come back to how we calculate that in a little while. But these other points out on the side are called the co-vertices. So you get a co-vertex and a co-vertex. Plural of which is co-vertices. And to get at them, we started at the center, and this one we went left and right, so we're changing that x coordinate. We were at 1, and we went left and right by this length, which we're going to call B. And we kept the y coordinate the same. So what these were at, where these were at, they were at 1. Well, 1 plus B, 1 plus 4, that's 5. And there was another one at 1 minus 4, which is -3. Let me look here, -3, -4, +5, -4. That gives you your co-vertices. So we've got to do some notes, and I'll come back and tell you how you work out where these foci are. Actually, why don't we just finish off these notes here? So our major axis was of length 2a. So in this example, it was 2 times a was 8. And our minor axis, going on this one that went side to side, it's of length 2b, it was 2 times 4, which equals 8. Now these foci, where they're going to be is they're going to be on the major axis, and they're going to be about there and about there, but obviously about is not good enough. We're going to say the length they are from the center. Because it's a focus, we're going to use C. Okay? Can you see from this picture that C is shorter than A? And how you actually calculate it, we get our A squared, the denominator, the bigger denominator. We have to make it shorter, so we're going to subtract the other denominator, and that will give us C squared. So to find C itself, the distance we actually want to the focus, we're going to have to take the square root of 48. And in this example, it's going to be a length a bit less than 7. How do I know it's a bit less than 7? Because 7 squared is 49. It's a bit less than 49, square root of 49. So I can draw them very easily by just counting 7 and going slightly less than 7. But how would I actually work them out? From the center, I'm going up and down by this square root, which simplifies, by the way, to the square root of 16 times 3. 16 times 3 gives you 48. So it simplifies to square root of 16 is 4. 4 times the square root of 3. Ugh. And I'm going up and down by that amount. So from the center, I'm going up and down, I'm going to change this by C. My foci are going to be at 1, and I'm going to get this -4, and I'm going to add to it, and I'm going to subtract to it our length C. So that's going to be at 1, -4 plus 4 times the square root of 3, and the second one will be at 1, -4 minus 4 times the square root of 3. They were much easier to graph than they were to write their coordinates. So that was taking you through a whole example of an ellipse, just working from an equation and teaching you the kind of notes and how you work with them as we go along, but you probably need some notes, so let's put in some notes. Put this on one page, split it down the middle. We're going to compare a horizontal ellipse with a vertical ellipse. Draw a reasonable size picture, and we're going to fill in all the details. So first of all, how would we know it was horizontal? How would we know it was vertical? Because you're just going to get an equation like this with numbers in it. It's not going to tell you this one's A, this A squared, this one's B squared. How you can tell is where the bigger number is. A squared will be bigger than B squared. That tells you which of your denominators is your A squared. This is for an ellipse. When we get onto a hyperbola, that is not true whatsoever. For an ellipse, it's all about the size. This one, it would be vertical because the number you would see here would be bigger than the number you'd see under the X. Okay? So that's what the equations look like. And when we're graphing them, the first thing we graph is our HK point, which is the center. Okay. And the center, you pull it straight from the equation. What is being subtracted from X? What is being subtracted from Y? Okay, that'll be the same for both of them. The next thing you would graph would be the vertices. Vertex here and here on a horizontal one, up and down for a vertical one. Now, how to get to those, the distance you're going to go from the center, we call it A. And how do you work out what A is? If you're going left and right, you look at what's underneath X and you get the square root of the number that you were given in the denominator. Okay? So on a horizontal ellipse, those vertices are going to be left and right of the center. This one's horizontal. The biggest number was under X. So we're going to change the X coordinate. We're going to get that H that's originally there in the center, and we're going to add or subtract A. So this will be H plus A and H minus A. And for a vertical one, if it's vertical, change the Y. So that Y, which is currently K, we're going to add or subtract A to that. So we'll leave the H as it is. Okay, so that's how to get to the vertex. To get to the foci, we're going to do exactly the same thing, but we're going to add or subtract C. On this one, we're changing the Y because it's vertical. We're going up and down. So let's put those on our picture. So, so this is the focus, and we've changed the X to get to them by C. And on this one, the vertical one, then everything important lies on the major axis. And remember, how do we calculate C? We get what we were given in the equation. The biggest denominator, subtract the smaller denominator, that will give you C squared. Those are your denominators. Then you take the square root of them to get your A and your B and your C to actually graph stuff. You have to square root everything. So, what we use the other denominator for? We call it B. And on the horizontal one, we'll go up and down by B to get to these points that are called the co-vertices. So each one is called a co-vertex. Oh, I didn't finish off the real center then. So how are we going to work those out if we don't want to just do it on graph? How do we work out the location of those co-vertices? Cool stuff. There's two of them. There'll be two of them on this one. Co-vertices. There's more than one. Okay, so if we went horizontally to get to the main vertices, we're going to go vertically from the center. So if we're going vertically, we're going to change that K. It's going to be K plus or minus B. Okay, and on this one, the actual main axis is vertical, so the minor axis will be horizontal. And if you're going in a horizontal direction, you're going to change the X coordinate. So you're going to get the H, and you're going to add and subtract B. So these ones will be, we're changing the Y. So this will be the same as in the center, different to the foci vertices. One will be a K plus B. And the other one will be H, K minus B. For a vertical one, we're not going to change the K, we're going to change the H, the X coordinate. And two last bits, these were the lengths, the height and the width bit. Your major axis is 2A, and your minor axis is the length 2B, and that's the same on both of these. Okay, so let's see if you can actually put those notes together. And let's see if you can graph one on your own now. Let me just check to see if you're asking any questions at this point. Okay, hopefully you've got those notes. Remember then, the main thing you look at when you look at the equation, you'll know if it's horizontal or vertical by looking for the bigger number. And then all the important points will be on that major axis. So we've just written all those notes. You've got all that. Oops, that's the one we've just done. We filled in all that information. Okay, so now you try one on your own. Here, you try this one. I'm going to pause the video and I'm going to give you 3 minutes, okay? Okay, so let's graph this one then. First thing to notice is that the bigger number is underneath x, so this one will be horizontal. The center will be at, you're subtracting -2, you're subtracting 1, so your center is at -2, 1. Then this number that's underneath x, that means take the square root of 9, it will be 3. So from the center, it's underneath x, so it's telling you to go 3 left and right. This case, point, I don't care which one's A and which one's B. This is under x, so it's telling me what to do horizontally. And 3 across, 1, 2, 3, 1, 2, 3. And then the number that's underneath the y squared, take the square root of that, and that tells you how far to go up and down. So we can draw this in. So the only thing missing from my drawing at this point is the foci. And I'm going to have to calculate those. And I actually want to write out all this information in the table as well. We always ask you about this. So because this was horizontal, to get to the foci, I'm going to change the x by c. So I'm going to have -2 plus or minus whatever that value of c is, followed by 1. So I'm going to have, oh, I don't know where they are yet, I haven't worked out c. And to get to my vertices, I'm also going to change the x by a. How do I know which one's a? The bigger one is a squared, so my a is 3. So -2 plus 3 would give me +1, followed by 1. -2 minus 3 gives me -5, 1. That, and I can check those points now. I've got one at 1, 1, and another one at -5, 1. You can check that from your graph. It's always good to do things 2 different ways and to check. To get to my co-vertices, I'm going to go the opposite of horizontal, so I'm going to change the y. So I had -2 and my y was 1. I'm going to add and subtract b to it. How big is b? B is this is the squared. So my b is the square root of it. I'm adding and subtracting 2 to the y coordinate of the center. So it's going to be -2, 1 plus 2 is 3, and -2, and 1 minus 2 is -1. So I should be able to check those points on my graph. Have I got -2, 3? Yep. And have I got -2, -1? Yep. You can check them on your graph. So we still haven't done the first side. We're going to come back to them. Now the easy part, your major axis is 2 times a. Your a is 3, so it's 2 times 3, which is 6. You don't have to show that work. Your minor axis is 2b. B was the square root of 4, which was 2. So I've got 2 times 2, which is 4. And again, you can check that on the graph. Check it as you go across there. Is that 6? 1, 2, 3, 4, 5, 6. Yep. Check your minor axis. Is this distance across here 4? Yes, it is. Okay, you can check all this stuff on your graph. You don't necessarily want that put on your graph like that, though. Now the foci. So this is the bit where you have to do a little sum. A squared minus b squared is going to give us c squared. A squared is your bigger denominator. B squared is your other denominator. Subtract those and you get 5. So that's c squared. So c itself will be the square root of 5. So, here on the right, -2 plus the square root of 5 for my x coordinate, 1 for my y coordinate, and I'm going to have -2 minus the square root of 5 for my other focal point. Now the graph one's easier than that. Just think to yourself, that's a bit bigger than 2. So from the center, it's horizontal, so I'm going to go left and right, a number a bit bigger than 2, about there and about there. When you're graphing, that's okay. Oh, label them with an F, focus. Okay, these points at the end are the vertices, and these ones here are the co-vertices going up and down. Right, so that was doing that part. Now we have to do the harder thing though. Graphing them and filling this information in. We can ask you multiple choice questions where we just ask you about, like, where are the foci on this? Do you have to graph the thing, whole thing? No. But it helps if you just sketch a little bit to actually think about where your foci are going to be. If we ever ask you to graph, we do ask you to write out all this information and we do check it. But what's going to be difficult is when you're not given them a nice graphing form like this. Okay? Everything's easy when you're given a graphing form. So I said at the beginning of the lesson, actually doing stuff where you have to create your own equation by completing the square, that's more difficult. Right. This is from question 3 of your homework. I'm not going to go over that now because that's a great one. That one's an easier one. I want you to do that one yourself. If you picked up a printout from school, question 4 was wrong. It was written, it was identical to question 3. So this is what your question 4 should say. If you haven't got a printout yet, you're going to look at the PDF on Canvas, and it's right. We've got the right question 4 on there. So don't worry about that now. But the PDF on Canvas is right for your homework. And these are really important practices. Let's go through this one now together. So we're going to use the same concept that I explained when we did with a parabola. You look along your equation and you see what is being squared. Well, on an ellipse, you've got both x's and y's being squared. So what you're going to do is you want any term that's got an x in it, so this one and this one, any term that's got a y in it, so this one, and group them and arrange them on one side of the equal sign, and anything else, which just leaves us with this, is going to go to the other side. So this is going to look very different from on a parabola, because on a parabola, only one of these was being squared. But, so what we're going to do, so this is just what you're thinking. What is being squared? On a parabola, it would only be one variable. On this, it would be both. So group all terms that are linked to the squared variable with those variables on one side of the equals. And as you're doing it, factor out any, if there is one, there might not be, any coefficient of the squared term. Okay, then you remove any variables that don't have a squared term and any constant. And on an ellipse, it's just going to be the constant. You move anything that you hadn't grouped like that to the other side. Move everything else. In this case, it's just going to be this one. Move everything else to the other side. So even though that concept is the same as how we did it for a parabola, it's going to look very different when we work with an ellipse. Then we're going to factor and complete the square. And for an ellipse, we've got to make it look like an ellipse equation. I'll talk to that when we reach that point. Okay, so you don't have to write out this every time. That's just what we're thinking as we do it. Oops. Come on. I'm going to erase those out of the way of my work. So the first thing I'm doing is I looked along and x's are being squared. So I'm going to group that term with this term, and I'm going to factor out that 8 as I do it. So I'll have 8 times x squared This plus 32, if I factor out 8, will become plus 8 goes into 32 4 times. Now it's going to be ready, let's set it up to be ready to complete that square. I'll come back to it in a minute. Then we're going to group, y is also being squared, so I'm going to group this and this. Yeah, adding it on, and I'm going to factor out that 2. So this one, if I factored it out plus 2, I'd be left with minus 2y. Now it's ready to complete the square because there's no coefficient in front of the y squared. You can't put these boxes in if you've still got a coefficient in front of the squared term. Everything else, and the only thing that was left was this. I'm going to add that. It was being subtracted, so I'll add it to the other side. But on this other side, I'm also going to have to add in those boxes. And we didn't just have one green box, we had 8 of them. And we didn't just have one red box, we had 2 of them. Okay, so now I'm going to factor and complete the square. I'm going to get this, and I'm going to factor and complete the square. So it's going to be 8 times something squared. How I complete the square is this will be x, half of plus 4 is plus 2. And what I have to put back in this box, I get that number, cut it in half, square it, put it back. 2 squared gives me 4. That needs to go in there. Now I do the same for this. So I'm going to factor that. Don't lose the fact you've got a plus there. 2 times, that would be y minus 1 squared. Half of that is negative 1. Square negative 1, you get plus 1. Put that on the other side. And now I have to put all of this together. Now, if you need to do a little bit of work, which I'm not in the mood to do this in my head, 8 times 4 is 32, plus 2, and that adds up to 10, 10. Okay, that's embarrassing that I had to do that, so let's burn the evidence. Eraser, that is not work I want to see on your sheet. Yeah? Pretend we could do it in our heads. Now, make it look like an ellipse. When you look at an ellipse, you always have x minus h squared plus y minus k squared over some number, and the bigger one of those is a squared. It always has to equal 1. So I've got to make that 200 become a 1. I can only do that if I divide the entire equation. So I'm dividing everything by 200. Now, 8 goes into 200 25 times. If you had 8 quarters, you'd have $2. 2 goes into 200 100 times. So my equation is x plus 2 squared divided by 25 plus y minus 1 squared over 100 equals 1. Is it an equation? Have you written an equal sign with something on both sides? Never ever don't bother writing that equals 1. You've got to say this equals 1, or you haven't written an equation of an ellipse. Now, we haven't got time to graph that, but on your homework, do please practice doing these on your own, because this technique is going to be the bit probably that you find the most challenging.